I suggested to you that we could find the moment of inertia of these concentric pulleys. But the problem with finding the moment of inertia of the concentric pulley is that what we know about moment of inertia has to do with mass and the distribution of that mass in an object. So basically what moment of inertia tells us is how difficult it is to change the rotational motion of an object. So like with these wands, these plastic wands, they have the same mass. If we just push them or like move them around in straight lines, they'd feel exactly the same. But as soon as we try to twist them from the center, the red one, it's a lot easier to change its direction, speed it up, slow it down, change direction, because all of its mass is concentrated right by where my hand is. The blue one, it's really difficult to do that because all of its mass is concentrated really far away. So when you're rotating things and trying to change their rotational speed, the speed with which they're spinning, or slow them down and stop them, that becomes way more difficult if the mass is far away from the center of rotation. So what we've talked about is the idea that, well, if we, like with certain things, we measure their mass and then we measure something about their size. And that works if the object in question has uniform density. So no matter where you look, the concentration of mass is the same, and it has some sort of a regular shape. We can essentially, for a sphere, calculate the average location of every point of mass if it's a sphere of regular size and uniform density. We can do the same thing with a cylinder or with a rectangular solid. We have to know where the axis of rotation is. In fact, we have done this for a whole bunch of regular, uniformly distributed mass solids. And so we so we can easily make a measurement of size, like how long is it, what's its height, whatever, and then we can make a measurement of mass by putting it on a balance, and that's all good. The problem is with these concentric pulleys, it doesn't work like that. With the concentric pulleys, there's a number of reasons why this is not an object that we can put on a balance and measure something about its size and figure anything out. One of the reasons is that this is not a regular shape. If you look at a concentric pulley, like from straight on, it's like a circle. If you look at it from the side, it's kind of like this weird pyramid almost. It's hollow in the back. There's like rings where the plastic is thicker, where the bands of the pulley are. I mean, basically, like if I were to say, what is this thing's shape? You would not be able to say, well, it's a pyramid, or a, you know, it's a rectangular solid or a cylinder. It's just a concentric pulley that's hollow in the middle. That's not like a shape that we have in the textbooks. The other piece that makes this really difficult is the mass is, first of all, it's made out of different materials. There's metal in this, and some of the metal is spinning. And that's, metal is in general more dense than plastic. So this actually has more mass concentrated right in the center of rotation. And even more importantly, a big part of the mass of these concentric pulleys is in the bar that holds them, and that doesn't spin at all. So that contributes nothing to the moment of inertia, which means we could measure the mass of this thing, and we could measure something about its size. We could measure the size of each of the pulleys. We could measure the radius and the depth, and we still wouldn't know what to do with that information to find moment of inertia. We cannot find moment of inertia by measuring mass and size for most objects, because most objects are not regular shapes of uniform density. So we have another way that we can think about this, because one way that we can find moment of inertia is if we have an equation that relates mass and size. We also have moment of inertia in Newton's second law for angular acceleration. So Newton's second law of angular acceleration says the sum of torques on an object, that is the like force plus leverage, the rotational force, the twisting force, will be equal to moment of inertia times alpha, and alpha is angular acceleration. So that means if we could make measurements for alpha, angular acceleration, and figure out the sum of torques acting on an object, then we can just do a division to figure out what that object's moment of inertia is. And that is where we kind of started on Wednesday. And what I had you do is think about, well, if we, so we made a few changes to our little system, because originally we were just hanging some paper clips off one end of these concentric pulleys. And the thing about that is it just worked crappily when we did that. And the main reason that it worked crappily is because the mass of the concentric pulley is large relative to the mass of a paper clip. The moment of inertia is large relative to the mass of a paper clip. And the string is like getting stuck in there. And if you've got a paper clip hanging off, this paper clip isn't creating enough tension in the string to cause it to unwind smoothly. So we figured out how to like hang some paper clips and measure alpha, but the alpha we got was crappy because it wasn't really uniform acceleration. So what I suggested on Wednesday is we can dial things in a little bit by placing larger masses on either side of our concentric pulley. One that's twisting it one way, one that's twisting it in the opposite direction. They're both pulling down. We get a much greater tension in both of the strings. The resulting acceleration, if we use the right masses, isn't going to be great. So we can still time it with our stopwatch, but the acceleration is going to be more uniform because the tension in the string means that it will both wind up on one side and unwind on the other side more smoothly. So, but we also were saying, well, we just need to find the angular acceleration. We didn't actually need to know anything about the motion of those masses. We played around with looking at the motion of the masses on Monday when we were looking at angular kinematics. But with this, we didn't really need to know anything about the motion of these two masses. We just wanted to know how quickly is the concentric pulley's speed changing. If we start it from rest and we hang some masses off of it, two sides pulling in opposite directions, let go, then how quickly does its speed change? And what I suggested on Wednesday was, well, if we count rotations, we can figure out how far this concentric pulley rotates in radians. That's our unit of angular measurement, because one rotation is 2 pi radians. So if you count rotations, multiply by 2 pi, we will get an angular displacement. And we have an angular kinematics equation that relates angular displacement to angular acceleration and time. And if the initial angular velocity is 0, this thing starts at rest, then we have a relatively simple equation we can use. We just double the angular displacement, divide by time squared, and that will be alpha, the angular acceleration. That will tell us how quickly this rotating object's speed is changing in radians per second squared. And if you did that, how many of you, just out of curiosity, on Wednesday, how many of you got a number for that? Raise your hand. Do you remember what it was? 8.73? That, yeah, so we'll look at that. That sounds low, but it could be right. Was it rotating really slowly? Oh yeah, so it only went around once. Yeah, okay, that could be, absolutely. Yeah. 14. Say it again. Alpha, the angular acceleration. You could have gotten a variety of numbers because this thing could be speeding up slowly or relatively quickly. What some people found was that they were getting angular accelerations of like 50 or even 100, which sounds like a lot, but it's really not. Because if this thing, like, let's say that you had it at the edge of a table and it unwound like 5 times as the mass, one mass went down and one mass went up, unwound like 5 times. Well, that's, so your math teachers would be very upset with me right now, but one rotation, which is 2 pi radians, is about 6 radians. So if it goes around, 5 or 6 times, that's basically like 30, 40 radians. And we'll like bump that up to 50 because this is physics, so we can bump, we can mush our numbers around a little bit. So that's 50, our angular displacement is 50. And if we double that, we get 100. And if our time was around 1 second, which is not ridiculous to think that this thing might have unwound in about a second, then we get an angular acceleration of about 100. And so if you got, less rotations than that and or a longer time, then it would be less. But I mean, angular acceleration of anywhere between like 10 and 100 to me would be reasonable. 10 would be about as slow as I would expect to see. 100 would be about as fast as I would expect to see. But it's not impossible to get different numbers. So that's great. And this is a relatively easy calculation to make. We can find the angular acceleration. The next piece, though, was to find the sum of the torques. And this is where we get back into and this is a everybody problem. It's not a just you all need to get this figured out, because every single person makes this mistake. Every physics teacher I know makes this mistake. We look at an object that is suspended from a string and we think, okay, I know the upward force on that object has to be the same as its weight. There's a string holding it up. It has a weight, gravity's pulling it down. We know it's the same force. And when we look at this type of an apparatus, like the first thing we think is, oh, the force in the string is the same as the weight. And so when we look at our setup here, our inclination is to say that the downward force acting at this point on the edge of the pulley on the left is equal to the weight of this mass, and the downward force acting on the right-hand side of the pulley is equal to the weight of this mass. And the problem is that's not necessarily true. It will only be true if there's no acceleration. If we have an object and it's not accelerating at all in any direction, then yes, the forces are balanced. There's only two forces vertically. Those two forces have to be equal and opposite. So in that case, the acceleration is 0, and the tension in the string will be equal to the weight, right? And then so that we can kind of map that force, like the tension is equal throughout the string. So the upward force on the mass is going to be equal to the weight. The downward force on whatever the string is attached to will also be equal to the weight. But in our system, the acceleration isn't 0. The wheel is spinning faster and faster, which means both of those masses are accelerating. One is accelerating up, one is accelerating down. The one that's accelerating up needs to have a greater tension than the mass, because if the forces are balanced, it won't accelerate. So that means the tension must be greater. And we can see that if we use a mass attached to a stretchy string. So if I accelerate this upward, you'll see my finger will move farther away from the mass, even as both my finger and the mass move upward. Just for a second, you can see that this elastic string stretch out. And it doesn't last long because I am too short to make this accelerate for a very long amount of time. And even those of you who tower above me still couldn't make it accelerate for that long. So if we really wanted to see this, the best way to do it would be with a machine, right? A machine that provides a constant upward force. Then we'd see the elastic stretches out as this object accelerates upward. If we have an object accelerating downward, then the gravitational force would need to be greater than the tension. That's easier to see because if we just allowed this object to accelerate downward, you will see this string become more slack. You can see it, right? Like there's a little ripple in it as I accelerate downward. For a brief amount of time, this object was in free fall. When it was in free fall, the tension was 0, and its acceleration was equal to g. Mass times acceleration was equal to mass times g. So, so we can't just look at this system and say, well, we know the downward forces. It's equal to the weight of the object. It's not. So how do we deal with this? What I said to you on Wednesday is don't, not yet. I said on Wednesday, just find the angular acceleration in radians per second squared, and then measure the mass on the left, the mass on the right, measure the distance of each mass to the center of rotation, and we'll figure the rest out later. So that's what we're going to do today, is we're going to start from where we left off on Wednesday. You had You had one of the pieces to finding moment of inertia, which is angular acceleration, alpha. Now we need to find the torque. The torque is ugly. And it's not ugly like conceptually. The math itself is ugly. So I'm going to walk you through this whole thing. You're going to end up with an equation. The equation is going to work. That's all we really care about. So what we're going to start with is recognition that we actually have three separate objects here. We have the concentric pulley, we have a mass on the left and a mass on the right. All three of these objects are going to be moving in predictable ways relative to each other. If the concentric pulley rotates counterclockwise, then the mass on the left will move up and the mass on the right will move down. Let's make all three of those directions positive. Mass on the left, mass 1, will have a positive direction of down. The mass on the right, mass 2, will have a positive direction of up. The pulley will have a positive direction of counterclockwise. That means that if our system rotates in the positive direction, then our mass 1 will move down and mass 2 will move up. The accelerations and the motion will all be positive. That makes things a lot easier to deal with. If yours rotated the other way, then what you'll do is just flip it. You'll just flip this around. I can explain how to do that, but I'll do that only if you need me to, because 50% of you should have seen something like this. So if we've got positive acceleration and positive velocity, then we can think about the torque on the left-hand side, the torque that's being exerted at this point right here. There's a force there. That force is some distance from the center of rotation. It's got some leverage. This is going to try to make this object spin in the counterclockwise direction. Torque 1 is going to be positive. Torque 2 over here is tending to make this concentric pulley rotate in the clockwise direction. So torque 2 is negative. All right, so our big starting point is this. The sum of the torques on this object will equal its moment of inertia times angular acceleration. We want to find the moment of inertia. We already know the acceleration, angular acceleration. We need to find the sum of the torques. So that's what we're working on right now, the sum of the torques. The sum of the torques on this object is going to be torque 1 in the positive direction plus torque 2. And torque 2 is in the negative direction. So we're going to just put a negative sign in front of it. This is the same convention that we used with forces. All our torques are going to be positive. And we'll put a negative sign in front of the variables if we know they're in the negative direction. So we're going to think of all torques positive, all forces are positive. We put a negative sign in front of those positive numbers to indicate direction. When we have a variable, we're going to set it up so that we know the variable is going to be a positive number. And then if we put a negative sign in front of the variable, we know that that would be a torque in the negative direction. All right, well, we have a general definition for torque. We know what the equation for torque is. The torque on any object at any point is the force being exerted at that location times the distance from that location to the center of rotation. So our torque 1 and torque 2 here have to do with the forces being exerted on the wheel. In the case of mass 1, that has to do with the tension in that string. In the case of mass 2, that has to do with the tension in that string. And tension 1 is being exerted at a distance of r1 from the center of rotation. So that means our torque 1 is going to be tension 1 times r1. And our torque 2 is going to be tension 2 times r2. I'm going to rewrite that because I wrote that r in a funny spot. So that means our sum of torque equations here is actually going to be equal to T1 times R1 minus T2 times R2. The tension in the left-hand string times its distance from the center of rotation, causing positive torque, plus the tension in the right-hand string at distance r2 from the center of rotation exerting negative torque. Okay, so the difference in those two torques is going to be the sum of the torques on this rotating object. Well, we just talked about the tension in the string and how it, like, what is intuitive is that it's going to be equal to the weight of those masses, but it's not equal to the weight of those masses. Both of those masses are accelerating. The sum of the forces on those masses is going to relate to the tension and the weight. The sum of the forces on those masses is going to be equal to mass times acceleration. How do we put this together given our strange reference system where we have down being positive for mass 1 and up being positive for mass 2? We just do it separately. The sum of the forces on mass 1 will equal its mass times its acceleration. It has two forces, tension, which is in its negative direction, and its weight, which is in its positive direction. So we put a negative in front of T1 and a positive in front of its weight. That's going to equal its mass times its acceleration, which we are going to engineer this situation so that its motion and acceleration are positive. So all of our variables are positive numbers here. If we solve this for T1, we get that T1 is equal to M1G minus M1A1. And we can do the same thing for the sum of the forces on mass 2. It's going to be equal to its mass times its acceleration. It has a different reference direction. Positive is up. So for mass 2, the tension in that string is in the positive direction. The weight of that object is in the negative direction. That will still equal mass 2 times its acceleration, which should be a positive number. So again, we are only going to put positive numbers in here. If we solve for T2, we get that it's going to be equal to M2G2 plus M2A2. So you can see we have different equations for T1 and T2, even though it's the same forces in the same real directions. And that's because we've incorporated all the directions in such a way that we only have to put positive numbers in here. We aren't going to have to put a negative acceleration or a negative G, like G will be positive, A will be positive, T1 and T2 will both be positive. And so we'll just, any number that comes out is going to fit with the scheme that we've done because of the way that we set up our reference frames. Okay, well, so the problem is that we still don't know the accelerations of these two masses. You could have found them because we know how to do that. If you measure their displacement and you measure the amount of time they take to move and apply kinematics, it's going to be 2 times the displacement time, divided by time squared. But I didn't ask you to measure that on Wednesday. I said, measure the angular acceleration of the concentric pulley and then just get the masses and their distance from the center of rotation. And that's because we can save ourselves a bunch of effort here and get much more accurate results by recognizing that while the mass on the left is going to have a larger acceleration than the mass on the right, they're both going to be related to the acceleration of the concentric pulley. The faster that thing is accelerating, the faster mass 1 will be accelerating down, and the faster mass 2 will be accelerating up. How do we know that? Because we tied together the acceleration of an object hanging from a string like this. The acceleration of this object is going to be equal to the tangential acceleration at the point where the string is attached. And the tangential acceleration of the point where the string is attached is related to the angular acceleration of the wheel itself. So for our two accelerations, we have these two equations. Our acceleration of the object on the left, A1, is going to be equal to the tangential acceleration at that point. And they will both be positive. M1 is moving in its positive direction. Our concentric pulley is rotating its positive direction. So the tangential acceleration is going to be positive as well. And we know that in general, alpha is defined as tangential acceleration divided by r. So if we just multiply both sides by r there, we get that the tangential acceleration on the left pulley in my diagram is going to be equal to alpha times the distance from that point to the center of rotation. And the acceleration at point 2 on the right-hand side is going to be equal to the angular acceleration times the distance from that point to the center of rotation. And the tangential acceleration will be equal to the acceleration of mass 2. So now we are only dealing with known quantities. We know the mass, we know g, we know alpha, we know r. That's all we need. So if we go back to our sum of torques equation, which is right here, let's see, our sum of torques equation is right here. The tension in string 1 times R1 minus the tension in string 2 times R2. We have the tension in string 1 right here, and we have the tension in string 2 right here. So that means the sum of forces, the sum of torques is going to be equal to T1, which is M1G minus M1A1 times R1. Wait, hang on. I gotta finish my substitution here. It's not A1, it's alpha times R1. All of that times R1, and then we're going to subtract T2, which is M2 G2 plus M2, and instead of A2, we're going to use alpha R2 because those are the same. All of that times R2, which is insane. But also, like, that's it. Like, we now know everything we need to know. So we're going back to our Newton's second law of rotation equation. The sum of the moment of inertia of our angular of our concentric pulley is going to be the sum of the torques divided by our angular acceleration. We already know angular acceleration. We just found the sum of the torques. If I do the algebra here, what we get is M1G R1 minus M1 alpha R1 squared minus M2 G R2, not G2, sorry, me trying to write and talk at the same time, minus M2 alpha R2 squared, all of that divided by alpha. And we know all these things. If you got an angular acceleration on Wednesday, then you know the angular acceleration, you know alpha. The masses, we use a balance to find R, we use a ruler to find, G is about 10, and we can find the moment of inertia. And that's it. So what I want you all to do today with the rest of the period is at least one of two things. If you got data from Wednesday, then you should be able to plug it into this equation and get a number pretty quickly. Maybe not like instantly, but reasonably quickly. And then what I want you to do, so these big concentric pulleys stink, right? They're no good. But we have some new pulleys in the back that actually hook up to your laptops. They're Vernier concentric pulleys. So what I want you to do, if you got data Wednesday, find the moment of inertia of the big concentric pulleys, and then we're done with those. Whether or not you got data on Wednesday, I want you to find the moment of inertia of the Vernier pulleys. And those are easier to deal with because if you hook those up to your computer, it can calculate alpha for you. You don't have to measure the number of rotations and multiply by 2 pi and multiply that by 2 and divide by time squared. You don't have to use a stopwatch. All you have to do is set it up on the computer and have the computer tell you what the acceleration is as this thing unwinds. So and then you can measure, you've got two masses hooked up to it, measure the mass of those two, measure the distance that the string is from the center of rotation, and you're in business. The tricky things about using the vernier pulleys are, first, you want to make sure, if you're going to use this equation, you want to make sure that all of your acceleration matches what I set up in this diagram. So the mass on the right needs to go up, the mass on the left needs to go down, and the pulley needs to accelerate and move in a counterclockwise direction. And the strings are real tangly. The diameter, the radius of the pulleys themselves is smaller. The strings are closer together. The pulleys themselves are way better. The engineering of everything is way better, but it's a lot more difficult to get this thing to spin freely because there's a much greater chance that you're gonna end up clonking your weights into each other, which stinks. There are actually ways that we could set this up with like some other pulleys that would make it easier to do, but we don't have time for that. And as fun as that would be, I think we can probably, with a little bit of practice, get a decent measurement for alpha, even without a super fancy pulley rig. So this is your job for today. And if you want to, if you have the data to first find the moment of inertia of the older concentric pulleys, great. But what's really important is that you walk out of here today with the moment of inertia of our new super fancy vernier concentric pulleys, because we're going to use those on Monday to test some predictions.